Hello, everyone. Good afternoon, and welcome to our final SeaWeek session for today. I've had lots of exploring about our marine environments, and we are going to continue that with our fabulous presenter, Phoenix from Fizzics Education, as they explore the deep blue oceans. So we've had a look at a lot of different marine environments, and now we are going to go down to the deep sea. So I'll hand over to you, Phoenix, and everyone enjoy.
Fantastic. Thank you very much, Karen. Now, a couple of things that I want to cover is we should be able to see there's a Q&A down the bottom. Should be roughly about here. So if you've got any questions as the show goes on, you can ask me a question, or if you want to reply to some of the questions that I ask you, you can type it in there as well. Another way that we can actually answer questions is using the raise hand button, and that should be about here if you're on a PC. So can I get everyone to just raise their hand for me? Fantastic. Looks like all of our friends' hands went up then. Perfect. So let's get stuck into talking about the deep blue ocean. So the ocean covers about roughly 70% of the Earth's surface. Now, if you were to go into a pool or into a large body of water and keep your head and neck above the water and your arms, all of your body that's below the water is about the same sort of amount of surface area as the Earth. Now, the amount of water that we've got, let's imagine that these two 5-litre buckets is all of the water on Earth, all of it. This is how much fresh water there would be. And then out of that fresh water, about that much is running water, which is not frozen. So all of the rest of the fresh water is caught and trapped in our ice poles and other things like that. And then out of this water here, that much is what we would call potable water or drinkable. It is safe for us to drink or to use for showers, things like this. So you can see how valuable of a resource water can be. And we're going to do a bit of a deep dive into the ocean. I've got another application on a screen that I'm going to share with you. And we're going to have a look through and see what we can find down deep. Now, let me get this stuff out of the way so I don't knock it off. And let's see. This app's a really cool one. You can check it out yourself at a later stage if you want. It's neil.fun/deep sea, and it lets you explore what's down. Now, as we go deeper and deeper, I want you to sort of take notice of the color of the background. So as we go down, you can see we've got things like polar bears are able to dive to this deep, the different sort of fish. Finding Nemo is over there. And we go deeper and deeper, and you might notice that there's a color change going on in the background, and we're going to talk about that soon as well. So we go deeper and deeper. So we're at the twilight zone now. So we keep on going and going. We've got some turtles and some sharks going this deep. Keep on going and going. Got the blue shark down here, firefly squid, big-eyed tuna, sea angel. They look a bit weird. So you might notice as we go deeper and deeper, the actual look of these creatures changes. And it's all to do with something called pressure. We're going to talk about that soon as well. Now we go deeper and deeper. Now this is a big sunfish, bamboo coral. Oh, look at these crabs. So some of these are bigger than a small car, just from their leg span. We keep on going deeper and deeper. So we're almost up to about the length of the Sydney Harbour Bridge. We've got these big whales that are able to go this deep. The leatherback sea turtle. Oldest sea turtle species. Interesting. Then we're down to the midnight zone. And so we're just over the length of the harbour bridge down. So many deep sea creatures cope by creating their own light, because if you've noticed, in the background, it's all black. None of the light can actually reach down this far. It gets absorbed or obscured by the water above it. So you can see with this anglerfish, it's got a little light above its head, and it uses that to attract its prey. All right, let's go a bit faster down. So this is the blobfish, and it took a long time for scientists to figure out that this is actually what it looked like. When it gets washed up on shore, it looks a lot more like one of the Pokemon that is able to replicate other ones. I forget what the name of it is. Ditto, that's it. We keep on going deeper and deeper. We've got the goblin shark. Now, the goblin shark is really quite interesting because it's got this long nose, and then its teeth are actually able to extend outside of its mouth. So it's able to catch its prey by pushing its mouth out and around them. Let's go deeper. Let's go a bit faster now. So we're about to looking at the hydrothermal vents. This is where we're able to get heat from the bottom of the ocean. Now, let's see, we're down to almost 2,000, 2 harbour bridges. Let's go a bit further. We should be getting up to, well, not very far away, we should see the Titanic. Let's keep on going. And you might notice that as we go further and further, there's not as many things that can survive down here. Scrolling further and further. So this one's pretty cool. Let's keep on going. Now, I don't want to scroll too fast, otherwise I might scroll past the Titanic, but we're almost there. Let's keep on going. They're getting more and more sparse. All right, so here we go. This is about the average depth of the ocean, but it does go deeper in some places, like the Mariana Trench. And we should have, there we go, the Titanic. So you might have heard of, there was a submarine that was going down to the Titanic last year and had a bit of a tragedy. Raise your hand if you heard that story. Yeah, okay. So we're going to replicate something similar to that using a soft drink can a bit later. So let's go deeper and deeper. This one's pretty interesting. Dumbo octopus. This is the abyssal zone. So very low temperatures down here. Keep on going. And you can see there's not really much down here. We've got a good old sea pig. Let's keep on going. And we're almost towards the end, I think. Actually, maybe not. Let's scroll a bit faster. So now we're down to the Hadal zone. Let's just keep on scrolling and scrolling. You're not really seeing much now. There are some things that still live down here, though, under immense amounts of pressure. Let's keep on scrolling. All right, so down here, deepest point of the Java Trench in the Indian Ocean. Let's keep on going. Wow, really, really deep now. I'm going to scroll much faster. Look at this. So we've got this submarine was able to go down into the Mariana Trench. And as of like 2012, there was only 3 people that had been down this deep. One was James Cameron, the guy that wrote the Avatar movie with the blue people, not the Last Airbender one. But now, because this technology is more available, I believe there's been over 20 people that have been down this deep now. We should be coming almost to the end. There we go. So it takes a long time to actually get down here. And the insides of these ships are really quite small because they've got to be able to withstand all of that pressure on the outside. So there we go. That's all of that. Now let's do a little bit of a demo to show what that pressure can look like. So I've got this tube here full of water and I've got some holes in the side. And the pressure that's above it, all the water is pushing down on that water, and we should see it come out at different levels. Now what I'm going to do is I'm going to try and capture this in the buckets so I don't get water absolutely everywhere. Let's see how far this top one moves. Now it's only got this much water above it. Oh, maybe it doesn't want to come out. Let's see if I can poke something in there. It really doesn't want to work for me. There we go. So we can see that it's coming out halfway into this bucket. Let's hold this up, make this one about the same distance. Try and get this one out. Don't know how my luck's going to go with this blue tack. It's seen better days. Let's try and push this one through. Maybe I might try skewer rather than the end of my pipette. There we go. We can see that that's now going almost to the end of that first bucket. Let's fill that back up. There we go. And then our last one has all of that water above it pushing down on it. There we go. Let's see if I can open that hole up with my skewer. If I can find it. There we go. Oh, it still doesn't want to open up. Got to really try and push it through. There we go. Oh, and it keeps on blocking up with the blue tack. Oh, there we go. Finally got it. So you can see that's going all the way into that second bucket, simply just because of that water above placing all of that pressure on there. So let's pop that back down. And success! I only managed to get a little bit of water everywhere. So let's explore the concept of pressure a bit more. And to do that, I want to use this thing here. This is called a bell jar. And it looks a bit like a bell, that's why we call it. But it's really strong at difference in pressure. So we need to suck all of the air out of this. And to do it, I've got down next to me this thing here. This is a vacuum pump. And it's able to work by sucking all of the air out of this chamber. So let's attach this on here. Make sure it's a good connection. Now this is going to be a little bit loud, so hopefully it shouldn't be too bad on the microphone. But let's try this. At the moment, that can move off. As soon as I turn it on though, that bottom stays on here. And this is because there's higher pressure outside, lower pressure inside. The high pressure wants to move towards that low pressure region. So let's squeeze this and take this one off if I can. There we go. And oh, we didn't actually get it locked off. Let's try that one more time. Oh, it doesn't want to seem to work for me now. There we go. And let's try blocking this off. No, it doesn't want to make a very good seal, but that's okay. We can move on to our next experiment with it. And for this, I'm going to use a balloon. about that big fine, maybe a little bit smaller. Let's tie it up. Now, my friends, I'm going to put this in here in a moment. I'm going to draw a face on it, but while I'm doing that, I want you to pop down in the Q&A what you think is going to happen to the balloon when it's in this vacuum chamber. Let me get a pen out. Let's see, what color Sharpie do I have? And let's see. Maybe we'll use a gold one. Excellent. Let's have a look at the Q&A, see what our friends are saying. Might expand, it might shrivel or pop. You think it might burst? Interesting. Now, you're going to have to be kind to me. I'm not a very good drawer. That's why I'm a scientist rather than an artist, but I'll give it a go anyway. And there we go. We've got our little guy there. Try and get him so he's facing the front. Make sure we attach this one again. There we go. Let's scroll through some of our Q&A. We think it might break, it might pop. Ah, interesting. Someone's been watching our Science at Home sessions, and so they have an idea of what might happen. All right, let's try it out. Now, I think we're starting to get a good vacuum in there. You can see that's slowly getting bigger and bigger and bigger. And then if I kept it going, it would probably end up popping. But we can see that there's a little bit of a leak in this chamber because it's starting to go smaller again. But we can let that air back in, hopefully. And there we go, it goes back small again. Now, the reason why this happened was because, well, the air pressure inside the chamber went low, and that meant that the balloon had higher pressure inside of it. So it wanted to push out into that space. Now, let's see what else can happen when we put it in our chamber like this. If we went really deep underwater, what can happen is there's gas in our bloodstream that can dissolve. And then as we come back up again, because we've got lower pressure around us than what was there previously, something interesting happens to those gases in our bloodstream. And to show you this, I actually need to get some soft drink. Soft drink has carbon dioxide dissolved in it. I'm going to get a cup. You can see that we've got some bubbles forming here already. So that's the carbonation. Let's pop it in here and let's zoom in a bit closer. There we go. We're going to turn our pump on and we're going to see what happens when we get this change to those dissolved gases. So this should start off pretty slow and then get faster and faster as we go on. Just make sure we've got a good seal. All right. Should be starting to get closer and closer to it. Looks like This tube wasn't on very nicely. All right, should be almost there. Now, what can you see happening to the bubbles inside? Pop it down in Q&A. What are you seeing on screen? We're going to keep this going for a bit longer. Yeah, it's bubbling. Is it bubbling a lot more than what it was before? All right, let's turn this off. And let's see if I can let this gas in nice and slowly so I don't knock it over. There we go. So now that is actually flat. We've actually gotten all of the carbon dioxide out of there. And what would happen in our bloodstream is anything like oxygen that's dissolved in there, other gases, will start to expand, turn into a gas again. And that actually causes a sickness called the bends. Now I've got another screen I'm going to share up. Let's go this one here. You've got some divers in this big chamber called a hyperbaric chamber. And what that does is it repressurizes and then lowers that pressure slowly. So then the gases can escape from their bloodstream without actually forming those gas bubbles. The bends can be quite dangerous. It's very painful. It can lead to joint pain, to fevers, and even death. So it's something we've got to be very, very careful of. Now, speaking of carbon dioxide dissolved in water, this can actually cause an acidification process. Looks like this might have been my leak from before. Let's pop that over here. Pop this one back on the ground. Now, the way I want to show this to you is I've got a couple of cups. I'm going to pour some water. And inside this, I'm going to put something called universal indicator. Universal indicator is able to measure if something is an acid or a base. Oh, that doesn't look like it's very strong. It looks like they're slightly different colors. This one's got a little bit more of a yellow tinge, so it must be that it's a little bit more acidic. So we can see on this color scale, if it's neutral, it's not an acid or a base, it's green. And then as it gets more and more acidic, it goes yellow, then orange, and then red. And if it goes the opposite of an acid, which is a base, it goes more like aqua, blue, violet, purple. Now, what I'm going to do with this is, let's start off with this one here. I'm just going to breathe into it. My breath has about 20% carbon dioxide in it when I breathe out. Let's zoom in. Let's see what happens when I breathe into it. Pop down in Q&A if you can see a color change happening. Almost out of breath now. I think that's about as much as my lungs are going to be able to handle. But yes, we did observe that it's gone more yellow. So it started to be more acidified. Now, this can actually happen to our oceans and to the rain if we have too much carbon dioxide in the atmosphere. And it can lead to some trouble with our coral reefs. I'm going to share a picture of some coral. And you can see we've got some coral there. And this acidification process can end up bleaching our coral and killing it off. So we've always got to be really careful about how much carbon dioxide we release into the air around us. All right. Now, my friends, who noticed the color of the background when we did our deep dive into the ocean? What color was it? It ended up going black, didn't it? So let's actually have a look at what can happen to light as it goes down through water. Now I've got some lasers. And let's see what happens when we put it in plain water. I've already put a little bit of salt in this, but we might need to put some more in there. You can see that the laser light goes all the way down the bottom. It's able to go all the way through. That was green. Let's try it with red. You can see that the light's down here. Now blue, you can actually see the beam as it goes through down to the bottom. Now let's grab a fork and some salt. Give this a good mix. There we go. Now let's try our laser lights in this one. Interesting, it doesn't seem to be reaching the bottom anymore. What about our red? Oh, that seems to be going a bit further than the green. And our blue doesn't really want to go very far at all. So different colors of light are able to move through the salt water different lengths, but ultimately they all end up being absorbed, or as a scientist would say, attenuated. Let's pop that there. And actually, I think we're going to use our plain water one. And I want to show you what happens with both salt water and hot water in our oceans, and how this can lead to the formation of currents. So for this, I need a couple of extra things. I need a couple of glasses. I need a syringe attached to a tube. Got some food coloring. I have got some super saturated salt water, and I've got some hot water as well. Now I think that might be a bit too much water in there, so let's just tip a little bit out. Probably about there is going to be good. Now the first one I'm going to do is my salt water. There we go, that should be maybe enough. I'm going to put some green food coloring in there. Perfect. Pop that off to the side, nice and neat. And let's get some of this in our syringe. There we go. So what I'm going to do is I am going to put this end of the tube about halfway down, and then I'm going to carefully, or very gently, squeeze on it. Now, what direction do you think this will end up traveling in? Pop it down in the Q&A. Will it go up or will it go down? Let's zoom that out a little bit and maybe move up. There we go. Well, we got some friends saying it might go up, some saying it might go down. Let's find out. Just carefully squeezing it out. And I don't know if you can see that well on camera, but we can see that's getting greener and greener down the bottom. There we go. I'm not going to do any more of that one. I think that should be enough. Let's get rid of all the rest out of there. There we go. All right, so because that water has a lot of salt in it, its density has changed. It's gotten much more dense. There's more stuff in the same space, and so it's much heavier. So it goes down. Now, with our other one, we're just going to use hot plain water. Let's undo this. Pour that in nice and carefully. Pop that over to the side. There we go. And get some red food coloring in there. Excuse me. Excuse me, I'm just going to have a sip of water. Got a little bit of a sore throat at the moment. All right, that's nice and red and pretty hot as well. Let's pop that over here nice and safe. And let's get some into our syringe. Now, can you predict when I put this in halfway, which way the hot water is going to go? Pop that in Q&A. All right, looks like we're ready. And let's see what our friends are saying in the Q&A. The hot water will go up, 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 up. All right, let's find out if that is correct. Now, I've got to be careful. If I push too hard, it will actually push the water down. So you can start to see that moving up. Got to be very gentle, very careful. There we go, almost there. And you were correct, it did go up. So that hot water is able to move upwards, and this is able to drive ocean currents around our planet. Let's zoom back out a bit more. Now, a lot of this heat that heats up some of our oceans is actually straight from the sun. Now, the sun's not always everywhere all at once. We've only got one side that's facing towards the sun. So we get warmer regions, and then towards our ice caps, we get colder regions. And so hot water creates higher pressure, colder water creates lower pressure, and we get these currents moving around. There's some really cool animations that you can find on some of the government websites around the world that actually show the movement of these deep ocean currents, especially south of Australia. All right, let's pop that off to the side there. And what we're going to do is we're going to do a bit of an example of our submarine. For this, I need a can. I'm going to get my hot water. I'm going to get a blowtorch. I'm going to get some tongs. All right, so I'm going to pop a little bit of hot water in here. And actually, I might put a little bit more water in here, I think. There we go. Now, the reason why we need to use hot water is we want it to turn into steam, we need it to boil, and that increases the pressure. And where does high pressure move towards? Pop it down in Q&A. I'm just going to put a little bit of water in there. Let's see what our friends have said. Yes, Millie, you're correct. It does move towards low pressure. Now, in the case of this, that lower pressure is out in the room around it, and you'll see the steam starting to move out in a moment. So we should start to see the steam moving on top. Takes a little bit of time to get it just right. Going a bit on the slow side. Oh no, it looks like my torch is running out of gas. Might just have to quickly grab another torch just off to the side here. Got another gas bottle as a spare. It's always good to have some spares around, just in case something doesn't go 100% right. All right, let's try this again. There we go. Now, once I've got this nice and hot and steaming, what I'm going to do is I'm going to turn it upside down and put the opening in the water. And that's going to seal it off. And it's going to cool it down. There we go. We should see that steam coming out. Not sure if it's coming up on camera that well. There's a lot. And when I turn this upside down in the water, it's going to happen really, really quickly. So we need to watch very, very closely. Look at that. It is a crushed can now. And the reason why that happened is because the steam that was inside cooled down, it condensed, it got a lot closer together, and we got low pressure on the inside. The higher pressure outside wanted to move into that space, and it actually ended up crushing the sides of the can. Now, if you remember last year, that submarine that was going down to the Titanic actually had something very similar happen to them, and unfortunately everyone on board lost their lives. It was a very big tragedy. All right, let's have a quick look through the Q&A. Fantastic. All right, now let's do another little experiment with our pressure, and for this I'm going to use some sultanas and some soft drink. Hopefully they should come up all right in the soft drink. Usually it's better to use something like soda water. Hopefully they'll be dark enough against the Fanta to see it. right, we'll pop a couple in there. And let's see, is it coming up on camera? There we go. They seem to go up and then fall back down again. And then they should go up, fall back down again. I might change to this camera off to my side and see if we can get a better picture this way. So you can see them going up and then down. Now, the reason why this is happening is these little gas bubbles of carbon dioxide form on any surfaces that are in there. And if they form on the surface of the sultana, what they do is they decrease its density and make it more buoyant. It goes up to the top, and that's where the gas can escape into the room outside, which then increases the density again of our sultanas. They go back down and back up. This is something that you can easily try at home. All you need is some soft drink. The clearer, the better, and easier it is to see, and some sultanas. We'll keep on going up and then back down. Alrighty, I think we might have enough time for one more experiment. And we're gonna, actually, before we do that, I want to show you a couple more pictures. Let's go back to here. Let's move this off to the side, and I want to show you this extra screen that I've got. Oh, where's my mouse gone? There it is. I'm going to talk a little bit about echolocation. So dolphins and some other creatures use echolocation to move about and stalk their prey. And the way they do that is they are able to create sounds that move out from them, and they reflect off anything around them. And when that bounces back, they're able to use a certain part of their brain, a special organ, to be able to detect those returning. And then by the speed of it, they can actually measure how far away something is. Now, they wouldn't think about measurement in the way that we do, as in like meters or kilometers, but they do have an innate sense of how far away something is. Another thing that I've got that uses something very similar is this Lego robot. On the front of this, it's got these two sensors here. These are called ultrasonic sensors. They send out a pulse of sound that's too high in pitch for humans to hear, and it bounces off something, bounces back, and it times how long that it is to get an actual measurement. And this can work anywhere from a couple of centimeters away to up to 2.5 meters away. Some other things can actually work further than that as well. All right. Now, just a quick question, Karen, do you think we might have time for one more experiment?
I think absolutely.
Fantastic. I want to do a little bit of a repeat of our experiment with the acidification, but instead of this time using my breath, I'm actually going to do a little chemical reaction to get 100% carbon dioxide. And so for this, I need a bottle, I need some bicarb soda, I need some vinegar. What I'm going to do is I'm going to put some vinegar in here. Being careful not to spill it everywhere. I reckon about that should be enough. Oh, do I have a hole in my bottle? I think I might. I'm going to have to swap over bottles, I think. Not to that one. Let's try this one. Let's get it in here. There we go. Chuck that one in the bin. Let's put a bit more in there because it seems to have just spread out all over my desk. All right, there we go. Now in our balloon, I'm going to put the bicarb soda. Just make sure it's nice and powdery. Oh, it's wanting to get stuck on me. There we go, got that through. Maybe I'll put a bit more in there. All right, that should be enough. Pop that lid back on so I don't spoil it. There we go. And let's pop this on here. Now you might have done some experiments at home where you mix bicarb soda and vinegar, maybe to make a fake volcano. We're going to get carbon dioxide as the reaction. All right, we're going to try and get all of this liquid back down the bottom. At the moment, it doesn't want to go down because we've got lots of carbon dioxide pushing up. There we go. So we finally got it all out. It's continuing to get bigger and bigger. All right, I think that's going to be enough. Let's get this off. I'm going to give this a little bit of a twist, and then I've got a little device that I 3D printed to hold onto this. So I'm going to pop it over the edge of this. Just going to make sure it's squeezed so that the air doesn't come back out. Let's squeeze it open. There we go, almost there. Let's pop this over the top. And then in this side, I can put my straw. No, it doesn't want to get in there. This did work nicely last time I tried. Maybe I had it around this way. There we go. Let's pop the straw in there. I might have a different size straw this time. That's okay, we can try it without the straw. I'm going to very, very carefully pop it in here. And try and let the air in slowly. So remember, this is all carbon dioxide. Let's see how quickly it changes. Let's zoom in on that. Can you see that color changing? And we've only used a little bit of the carbon dioxide in that balloon. Almost all the way through. Let's see how much we can get the color to change. I'm making a huge mess in here, but that's okay. It's not fun unless you make a mess. And look at that. What color did it change to? It's changed a lot faster, isn't it? And it's way more orangey red than what it was with just my breath. All right, my friends, that was my final experiment. We've gone a little bit over time, but I was having so much fun. I'm going to hand you back to my friend Karen.
Excellent. Thank you so much for that, Phoenix. I'm loving all the experiments, and even just being able to see that water separation still there and the acidification. Very, very interesting, because when we're thinking about SeaWeek, we also need to think about how we can protect and look after our marine environment. So we need to think about how we avoid getting some of these things in our marine environments, and thinking about ocean currents and how important they are for the temperatures of our ocean. So many amazing different things to consider. So thank you so much for joining us today, and thank you everyone that has been part of our SeaWeek presentations today. And we have When the Rivers Meet the Sea tomorrow. So thank you all very much, and we'll see you again later. Bye, everyone.
Bye-bye, everybody.